This diagram shows a side-by-side comparison of a theoretical model and a physical reality. On the left, we have a non-deterministic finite automaton, or NFA. It is easy for us to design because it allows a single input to branch into multiple possible paths. On the right is a standard computer processor. Processors cannot guess or handle ambiguity. They require absolute determinism to function. To get from human-friendly design to machine-readable execution, we use an algorithm called the subset construction method. This method translates the branching logic of the NFA into a strictly deterministic format. This animation demonstrates the core rule of the algorithm. We take the potential combinations of multiple NFA states, like Q0 and Q1, and merge them into a single, unified state in our new deterministic finite automaton. By treating a set of multiple potential paths as one distinct reality, we eliminate the ambiguity. The machine no longer has to choose between paths. It simply moves to a new destination that represents all of those possibilities at once. This visual shows a complex NFA state diagram. While circles and arrows work for simple concepts, they become impossible to track during a complex conversion. The very first step is to translate this diagram into a standard transition table. We begin building our new machine by pulling over the exact start state from the NFA, in this case, Q0. The algorithm evaluates where Q0 goes on input A. Since the NFA transitions to both Q0 and Q1, our new DFA creates the composite state Q0Q1 and writes it into the new table. Evaluating this initial state acts as the catalyst for the entire process. The new composite states generated in this first row will dictate the exact subsequent rows we need to calculate, driving the rest of the algorithm forward step by step. To determine where our new composite state goes next, we look at its individual parts. We take the mathematical union of Q0's transitions and Q1's transitions. By combining the destination cells from both rows on the original table, we populate the exact destination for our new DFA state. A strict deterministic machine requires every state to have a mapped output for every possible input. If an NFA path hits a dead end, an empty set, we solve this by creating a trap state. This state loops back into itself, capturing invalid inputs without breaking the strict rules of the DFA. The combination of the union operation and explicit trap states covers every edge case. Every single input now has a defined path, ensuring the machine operates with absolute certainty. Now look at the NFA table on the left. What is the transition for the composite state Q1, Q2 when given the input B? Pause the video and calculate the union. If you took the transitions for Q1 on input B and unioned them with Q2 on input B, you get the correct destination state. With the table populated, we need to assign our accepting states. Look back at the original NFA final state, Q2. The rule here is strict. Any composite state in our new DFA that contains Q2 becomes a final state itself. We mark each one with a double circle. This rule preserves the logic of the original non-deterministic model. Since an NFA needs only one successful path to accept an input string, our DFA accepts any composite state where that successful path is present. This final visual shows our completed transition table taking shape. We can now translate these rows and columns back into a physical machine. The resulting state diagram is complex, but it possesses the absolute determinism required for actual computation. This diagram is your subset construction cheat sheet. First, convert to a table. Second, let the start state initiate the new rows. Third, use union math for composite transitions. Fourth, route dead ends to a trap state. And fifth, carry over the final states. By breaking down the ambiguity step by step, we convert theoretical freedom into mechanical precision. Algorithms like this allow us to build systems that are as reliable as they are complex.